This is the View Calculus class. We're doing topic 6, which is the product rule and learning the trig derivative rules. So let's start with the product rule. So let u and v be some functions of x, right? So u and v are functions of x, like x, for instance, u could be x squared and v could be 3x to the fourth, because that's what we're about to do. The derivative of the product u times v is u dv, meaning u, the original function just as it is, times the derivative of v, plus v, the original function just as it is, du, the derivative of u. That's called the product rule. So what we're going to do in example 1 is we're actually going to differentiate something that we would never use the product rule for. In a minute, I'm going to show you examples where you actually would use the product rule. Here, it doesn't make sense to use it, but it technically is mathematically right. It's just not the best way to do the problem. So let's differentiate f of x equals x squared times the quantity 3x to the fourth two different ways. We're going to do it once with the product rule and once by simplifying first. So if I were going to do this as the product rule, and it is a product, I can use the product rule. There's no rule that says I can't. It's just not the more effective way to do this problem. So my u is the first function, the x squared, and the thing it's multiplied by is my v, the 3x to the fourth. So f prime of x, using the product rule, should be u, so u exactly as it is, x squared, dv, right? dv would be the derivative of the 3x to the fourth, which would be a 12x to the third, right? Plus v, which is 3x to the fourth, exactly as it is, du, which would be a 2x, right? If I clean this up, I get 12x to the fifth plus a 6x to the fifth, so I get 18x to the fifth. And that's fine, and totally the right answer, okay? But you'll see in a second why it would have been much faster to simplify first. So I got that f prime of x is an 18x to the fifth. Totally right. Let's do it the other way, though. If instead of deriving first, I take my x squared times this 3x to the fourth and just clean it up a little and make f of x equal to a 3x to the sixth, because that's what would happen, now I derive, right? So now I derive. And when I do that, I get my f prime of x is, I drop the 6 down in front, so 6 times 3 is 18, and I lower the power by 1. Oh, look, there's my 18x to the fifth. Same answer. Both methods are correct. One of them is significantly faster. So if we can do that, you might say, but Hogan, why would I even use the product rule then? That is a very good question, my friend. The answer is, you would use the product rule predominantly for products that cannot be simplified. The reason we were able to simplify this is they were both powers of x. So x to the third times x to the seventh is next to the 10th. Great. But what if one of the functions is something like an x squared and the other function is a trig function? X squared times cosine x is not so pretty, and you won't be able to do that. You can't simplify. So in order to show you how to actually use the product rule, I need to teach you a couple other derivatives first. So we're going to learn the trig derivative rules. So when I said that at the beginning that you learn the long way to do the derivative, but in reality you're going to memorize a bunch of rules to help you do derivatives quickly, the 6 trig derivatives are super important and you're going to need to memorize them. I would suggest making note cards for them, right? So let's walk through them. The derivative with respect to x of the sine of x is cosine x. The derivative with respect to x of the cosine of x is negative sine. We'll talk about how that creates a loop in a minute. The derivative with respect to x of tangent x is secant squared of x. The derivative with respect to x of cotangent x is negative cosecant squared of x. The derivative with respect to x of secant x is secant x tangent x. Sometimes we just say secant tangent, but you have to write the x's. And the derivative with respect to x of cosecant x is negative cosecant x cotangent x. And again, we sometimes just say negative cosecant cotangent, but when you write it, you have to make sure you include the x's. Okay, so these are our 6 trig derivative rules. You should make note cards where one side of the note card is the derivative part and the other side is what, like, one part says the derivative of sine with respect to x and the other side says cosine, okay? At some point, we can chat about a cool little looping thing that happens with sines and cosines. You can imagine that since these guys kind of work in a loop and derive, eventually you get back around to sine itself. In fact, actually, forget the at some point. Let's just do it real quick now. Let's say I start with sine and I derive. Okay, so down for derive. The derivative of sine is cosine. The derivative of cosine is negative sine. If I derive negative sine, it would just be the same as deriving sine, but with a minus sign in front of it, so it would be negative cosine. And guess what? If I derive negative cosine, right, when you derive a cosine, you get a sign of the opposite sign. So I'm going to get positive sine, and what I want you to notice is it looped back to the start. So it's a loop with 4 terms. So I could actually ask you to find like the 2000th derivative of something, because if you notice that it's a pattern, that it's just going to keep looping like this back to the next thing, which is pretty cool. So anyway, we're not going to do anything with that looping, but it's a pretty cool thing to know, and it's something that'll probably come up in your regular calc class. So now that we have these trig derivatives that I'm going to leave there so that we can use them as we walk through our examples, let's go ahead and actually use the product rule in a meaningful way. So in example 1, it's not that you didn't use the product rule correctly, you totally did. It's just that no sane person would pick the product rule to do example 1. But here you have no choice. So if you're asked to find f prime, right, so again, in all of these, we're finding f prime, right? That's what we want. So if we're asked to find f prime, here I have x squared times the sine of x. There's nothing I can do to not make this a product. My u is the x squared, my v is sine x. So when I want f prime of x, I'm going to have to do u dv, derivative of sine is cosine, plus v, which is sine of x, du, which is a 2x. It's important that you note that this 2x is not inside the sign. So my answer ends up being x squared cosine of x plus 2x sine of x. Because again, this was u dv plus v du. And there's no other way to get this derivative other than using the product rule, right? You have to know how to do the product rule to do this. I mean, okay, that's sort of a lie. You could actually do it weirdly with a quotient rule if you did something crazy, like make this an x the negative second on the bottom, but that'd be a terrible life choice. Trust me, this is the way to do it. All right, so let's do an example 3. F of x is 4x to the 5th times the tangent of x. So yet again, I have 2 functions that are both in terms of x but can't be combined. You could put the 4 with either of them. I would suggest that you just leave the 4 with the x to the 5th. It's much easier. So then my f prime of x is going to be u, which is 4x to the 5th, dv. Well, the derivative of tangent is secant squared, right? So u dv, so secant squared, plus v, which is tangent x, du is going to be a 20x to the 4th. So my answer ends up being that f prime of x is 4x to the 5th secant squared x plus 20x to the 4th tangent x. All right, cool. We have, I think, 5 examples. So we'll call it quits on this, and then we'll do 4 and 5 in the last video.